It's going to be a challenging question. We're supposed to use L'Hopital's. Okay, so let's be clear. What is L'Hopital's rule? It says when you have 0 over 0 or infinity over infinity, then take the derivative of the top and the bottom separately. And that's the key word, separately. Okay. So let's take our function. Let's just plug in the 1 first, right? X is going 1. So let's plug in 1, plug in 1, plug in 1. What do we get? Natural log of 1 over 9 to the natural log of 1. That's weird, a little weird looking, huh? Minus 1. So, okay, what's that? Now, do you know what the natural log of 1 is? Let me help you with that. Natural log of 1 is 0. Let's see it on the Desmos calculator. Natural log, go to the function. Where is it? There it is, natural log. Back to the numbers, 1, boom, see it, 0. So natural log of 1 is 0, so we get 0. And this is 9 to the 0 minus 1, right? Because the natural log of 1 is 0 again. So that's 0 over 1 minus 1. That's 0 over 0. Now, what is 0 over 0? It turns out it's indeterminate. You might think, no, it's 1 or it's 0 or something. No, it's just unclear. It's what we call indeterminate, meaning we can't determine it. You think, well, yeah, 0 on the top is 0. Yeah, but 0 on the bottom is infinity, right? And the whole thing might be 1. It's just unclear. It depends on a lot of things. We say it's indeterminate form. It's rules in conflict. It's unclear. So what do we do then? Well, when you get 0 over 0, you take the derivative of the top and the bottom separately. You do Lopez. So use L'Hopital's rule. Here we go. The way a lot of people say that they put an H over there, you're saying I'm on the next step, I'm using L'Hopital's rule. You don't have to. It's kind of tradition, though. There's a few traditions in calculus. Okay, so here we go. Now, this is going to be a little tricky because these are not easy derivatives. How do you do the derivative? How do you do the derivative? What's the derivative natural log of x? Well, that's 1 over x. That's not bad. Right. Okay, but now what's the derivative of this part? What's 9 to the natural log of x? Yeah, that one is bad. Okay, so remember how to do that. So let me remind you. That's an exponential function. So if we have something like x to the 9, let me just do a little talk about this. I know that's not what we have. Then that's just the power rule. 9 just comes down 8. Boom. But if we have 9 to the x, oh, that's different. What's that derivative? Well, it's like e to the x, right? Because the x up in the power zone. What's true of e to the x? Well, he's our favorite one. He does nothing, right? And so 9 to the x is like that. Whoops, not 9 times x, 9 to the x, right? At first he does nothing, but times the natural log of 9 because he's not the perfect number. Are you tracking with me? Now I know you might say, Miss, we don't have 9 to this. I know. I'm building up slowly. I'm going to get to 9 to the natural log of x in a second. I'm kind of building slowly. Right? So again, if the x was in the base and the number in the power, that's the power rule. Just bring the 9 down, subtract 1, piece of cake. But when these guys are called, these are both exponential functions. Because why? Because x is an exponent. See, x is up here in the power zone. X is up here in the power zone. So, that's different than when x is in the base. So when x is up in the power zone, that's like e to the x. He's the classic exponential function. He's our favorite derivative. He does nothing. So 9 to the x or any other number to this is similar. At first, it does nothing. But because 9 is not the perfect number, then you got to have this little adjustment times ln of 9. That's not chain rule, right? The inside is just a simple x. That's not chain rule. That's adjustment required. Okay, great, got it. Right, but now to make matters worse, oh, I lost the problem. Um, we have um, we have 9 to the natural. What's that going to do? Well, let's do it carefully. The derivative. Oops, I'm just kidding. Let me get a little more room here. So 9 to the natural log of x. Well, he's our favorite one. He does nothing at first, right? Does nothing. Times the ln of 9. That's not chain rule. That's just adjustment because he's not e to the x. He's not the perfect number, the 2.7, whatever. But then There's also chain here because the inside, funny, whereas here, inside was simple x, done. Here, the inside is not a simple x. And so I got to do the chain rule. What's the root of natural log of x? 1 over x. Ah, all right. So there we go. All of that, back to it. All that's the derivative of 9 to the natural log of x. It does nothing at first, times natural log of 9 for the adjustment, times 1 over x for the chain rule, right? That's the chain rule there. All that minus 1, because derivative of x is 1. There we go. Tough derivative. Okay. We did it. We did the derivative. Now, um, x is going to 1, right? So let's plug in a 1. Plug in a 1 here. Plug in a 1 there. Let's see what we get. Hopefully we'll get something good. So what do we get? 1 over 1 on the top. We're going x going to 1. Plug in 1. 9 to the natural log of 1 times natural log of 9 times 1 over 1 minus 1. A lot of 1s. Can we clean that thing up a bit? 1 over 1's 1. What's natural log of 1? We looked it up in the calculator a minute ago. That's 0. Natural log of 9. 1 over 1's 1 minus 1. Close. A lot of 1s. Just be careful. It's 1. 9 to the 0 power, that's 1 amidst all the other 1s. Okay? Almost. The top is a 1. 1 times natural log of 1 times 1, that's natural log of 9. Yeah, let me make that better. Heck, let me even put parentheses there. Natural log of 9 minus 1. There's our answer. You can type it in just like that. That's they want an exact answer, doesn't want a decimal. So type it in just like that. There we go. So what did we do? We did Lopi. We tried just plugging in the 1 in the beginning, but when we did, just plug in 1, plug in 1, plug in 1, we got 0 over 0, which is unclear, indeterminate. So we did Lopi's. We drew to the top separately. That was easy. Now, again, that's not chain rule, notice. I'm not, you might want to miss you didn't do, I'm sorry, it's not, let me try that again. It's not quotient rule. It's not, you say, this is a fraction, I got to do quotient rule. Well, no. No, I'm doing L'Hopital's rule. L'Hopital's rule is not quotient. Quotient rule, they take turns, you divide by the denominator squared. I'm not doing that. I'm doing Lopi. And what does L'Hopital's rule say? Derivative the top bottom separately. Just top all by itself. Done. Then the bottom, that was a tough derivative right there. He does nothing. The adjustment, ln9, and then chain rule, derivative the inside, 1 over x. And then we plugged in the 1, worked everything out, got our answer. So there we go.